Make sense? I think those calculations are pretty straightforward. So now we know the genotype frequencies we'd expect at Hardy-Weinberg equilibrium. So imagine our kit fox population. Let's say that perhaps it has experienced some form of fragmentation. So perhaps a housing development or a fence has gone through our population and separated it, and that's reduced the likelihood of random mating among individuals. So we'd expect some kind of deviation away from Hardy-Weinberg, which assumes random mating. So this deviation here can be quantified. We can estimate the amount or index the amount of deviation away from Hardy-Weinberg, and we do that through something called an F statistic. And the F statistic is sometimes called an inbreeding coefficient. So let's have a look at how it's calculated. So the inbreeding coefficient, or the F statistic, is really a pretty easy calculation. It's quite straightforward. And it's given by this equation here. So F, our statistic of interest, is this term H naught, H sub 0, minus H divided by H sub 0, or H naught. Sounds pretty straightforward. Well, what the heck is H naught and what is H? H naught really refers to the expected amount of heterozygosity in our population. So that's what we expect. And that's something, of course, we derive from Hardy-Weinberg. That's the expected proportion of our population that we anticipate will be heterozygous. The H term is really what we observe in our population. So H here is the proportion of our population that are indeed or are in fact heterozygotes. And we then divide that by the whole thing by H naught. So what sort of values do we expect with our inbreeding coefficient? Well, we expect values to essentially range from 0 to 1. So somewhere along this continuum. And this gives us a measure of the effect, the strength of inbreeding in this population. So what is a 0 value? What would we expect 0 to be like? Well, if we had a 0 value, that would mean that we would have the same number that we expect in our population actually being observed in our population. So if we had 50% expected rate of heterozygotes and 50% actually observed, then the numerator here becomes 0, and when that happens, our F statistic becomes 0. So a 0 value here would mean that we're meeting the conditions with respect to mating of Hardy-Weinberg. So we'd expect random mating when we have a 0 value, or a value that's close to 0. Now let's look at the 1 side of things. If we had a value of 1, an F statistic value of 1, we're really expecting quite the opposite. So if we had 50% heterozygotes expected, and in fact we had very few of those heterozygotes actually observed. Let's say we had 0 observed. If that was the case, then we really just have H naught divided by H naught, which of course is a value of 1. So in this case, when we have a value of 1, we are expecting not random mating, but really complete inbreeding. Let's jump back to our kit fox example, just put a couple of numbers in there. We know that from our kit fox example, we expected, based on our Hardy-Weinberg calculation, that the frequency of the A1, A2, the heterozygous zygotes in that population, to be 0.48, or we expected 48% of them to be heterozygotes. Well, let's imagine that we observed 0, just to again demonstrate the F statistic and the 0 to 1 continuum. So we didn't observe any of them. We had breeding occurring that expunged or did not result in any heterozygotes being born and continuing in that population. So if we apply our equation, or we add those numbers to our equation, we have 0.48 minus, so that's our expected, that's our H naught, minus what we observed, which is 0, all divided by H naught, which is 0.48, which then gives us a value of 1. So as I mentioned before, when you have a value of 1, you have a high measure, a high amount of inbreeding occurring. So this is inbreeding. And again, just to add to it, we'll now look at the opposite situation. Again, with our kit foxes, if we had a 48% expected rate of those, or frequency of those carrying the heterozygous form A1, A2, and we actually observed 48% of the population being that particular genotype, then our F statistic is 0.48 H naught minus 0.48. This is our H value divided by H naught, which is 0.48. And that gives us in the numerator here a value of what? It gives us a value of 0, which means that our F statistic in this case ends up being 0. And in this case, we would have random mating. Easy enough, yeah? One last piece here. If we consider the case of outbreeding, what would we expect our F statistic to look like? What would outbreeding result in? Outbreeding, of course, causes more heterozygosity. So in that situation, if we had outbreeding occurring, we would simply have a higher value of H. H would be greater than what we expected. So if we had, in our kit fox example, we had 0.48 as our expected frequency of heterozygotes, but we actually observed a higher proportion. Let's say we observed 53% of our population being heterozygotes, which might occur through outbreeding, and we divide that now by H naught, 0.48. What does that give us now? It gives us 0.05 in the numerator divided by 0.48. And what does that end up being? I guess this is the key point. That ends up giving us the value of negative 0.10, if I've done the math correctly. Negative 0.10. The key point here is that outbreeding will result in negative F values. So we're now on the other side of 0. Negative values are indicative of outbreeding. So how do we interpret this range? Right? We have a range of 0 to 1. What do numbers within that range actually mean? Well, a 0 value would indicate what now? A 0 value would indicate completely random breeding. Why would that be? Well, think about the equation. Specifically, think about the numerator. If we had completely random breeding, completely random mating, we would have our observed values, our observed amount of heterozygotes here, being the same as what we'd expect by Hardy-Weinberg. So those two components would cancel each other out in the numerator, and we would have a 0 value in the numerator, which would give us an F value of 0. Easy enough. So if we have the observed matching the expected, what we see matching what we'd expect at equilibrium, our F statistic will be 0. At the opposite end of that range, we have 1, and that would indicate a situation in which we have complete non-random mating. So in this circumstance, we would have nothing but homozygotes in the population. So let's jump back to our kit fox example and calculate F.
But this time what I'd like to do is focus on a slightly different kit fox population. One that has a few different numbers just to make things easier and a little more straightforward to follow. So let's imagine we're studying this kit fox population that lives in some isolated valley. And what we're interested in doing, of course, is calculating the F statistic for that population. But before we do that, what I'd like to do is estimate the genotype frequencies and allele frequencies, just to make a really key point about the relationship between the two under a scenario of inbreeding. And this is a point, again, that will come up in the spreadsheet exercise that will follow shortly. So let's look at this population now. We're interested in estimating genotype frequencies. So we have a particular gene that has two alleles. It has the A1 allele and the A2 allele. And there are three genotypes in this population. There is the A1A1 genotype, the homozygotes, the A1A2 genotype, the heterozygotes, and then we have the A2A2 homozygotes as well. So three genotypes in this population. This population, our starting population, has a total of, 1,000 individuals. Now we're going to assume that these individuals pair up, they mate, and they produce offspring. So we have, in the next year, a new crop, let's say, of 1,000 individuals. So this is the new generation. These are all the offspring that have been produced. So the question is, with a certain level of inbreeding, what do we expect in our next population? Okay, so what do we expect? If we have 500 heterozygotes, would we expect that same proportion to occur? Would we expect about 500 to occur in the population of our next generation? Probably not, right? We've talked about this earlier. If inbreeding occurs, we would expect a reduction in the amount of heterozygosity in that population. So we're going to assume now that some form of inbreeding here, some form of non-random mating occurs that results in inbreeding, and that drops the proportion of heterozygotes. So we're going to say arbitrarily that in the next generation we have 300 individuals then that are A1, A2, that are heterozygotes. And we'll say our homozygotes remain the same. So we've got, in this case, 350 A1, A1 and 350 A2, A2s. Okay, so again, we've reduced the amount of heterozygosity in this population. Now, let's have a look at the allele frequencies of this population. How do we go about calculating allele frequencies? We'll do it actually for our first population and then our next generation. So how do we do that? Remember how to calculate allele frequencies? We covered this a little bit earlier, and we also covered it in some earlier modules. So that would be 2 times, at least for A1, 2 times the A1 homozygotes plus the number of heterozygotes divided by 2 times the number in our population, which is 1,000, right? And for A2, we would have a similar equation. We would have 2 times the A2 heterozygotes plus, homozygotes plus our heterozygotes, all divided now by 2 times 1,000, or the number of individuals in our population. So remember, with allele frequencies, we're looking at the total number of alleles of any kind in the population. So we know that each individual carries 2 alleles, right? So there's 2,000 alleles out there. And we know that for every single A1, they carry, each one carries 2 copies. So we're multiplying by 2. And then, of course, we have to add the number of heterozygotes because they each carry 1 copy of A1. So just as a recap, this is the equation for estimating allele frequencies for, in this case, the A1 allele. And that should give us a value of 0.5. For our A2 allele, then, we should have the same value, 0.5. We've calculated much the same. Now, let's do that for our next crop, our next generation here. We've got 2 times the A1 A1s, of which we had, if you recall, 350, plus 300 heterozygotes, all divided by 2 times 1,000. We had 1,000 individuals in the next generation. Same would be true for A2. We have 2 times 350 plus 300, all divided by 2 times 1,000. So, if I've done the math correctly, we should end up with a value that is 0.5 for each one of these. Aha! So what do you notice here? If you look closely, we have the same allele frequencies. So in this case, we have caused inbreeding to occur artificially here in this simulation. We have simulated inbreeding. That has reduced the number of heterozygotes in the population. But what that's done is had almost no effect really on allele frequencies. So genotype frequencies have kind of gotten out of whack, right? So they have changed from what we would expect from Hardy-Weinberg. They're not the same. That inbreeding has changed those genotype frequencies such that we have fewer heterozygotes in the population. But the allele frequencies now have basically remained the same. So that's a key point to remember, and one that we're going to come back to in the spreadsheet exercise. So let's move ahead and go ahead and calculate F for our population of kid foxes here. Let's calculate that F statistic. So here we have on the top the same data that we started with. We've got our first year and our second year, and those numbers should look familiar to you. So if we want to calculate F, the first thing I'm just going to do is I'm going to estimate proportions of genotype frequencies, not just number of individuals, but proportions in our population. So I'm going to divide each one of these numbers by 1,000. Easy enough, right? Divide by 1,000 individuals. And you can probably do this math in your head very easily. This would give us 0.25. This would give us 0.5, 0.25, 0.35, 0.3, and 0.35. Got it? Easy enough. Okay, so to calculate F now, remember that the equation is H naught minus H divided by H naught. So H is what? What does H represent? That's the proportion of individuals that are heterozygous or heterozygotes in our population. That's our proportion of A1, A2s. So let's focus on the recent generation now, the one that has resulted from inbreeding. What is our H value? Well, let me jump back a page. Our H value then would be 0.3. That's the proportion of this genotype in our population. So that gives us 0.3. Now what is H naught? So H naught, remember, is what we would expect, not what we observed. This is our observed value, but what we actually expect under Hardy-Weinberg. So how much or how many or perhaps what proportion of our population do we expect to be heterozygous? Okay, so how do you calculate that? Well, think back to that Hardy-Weinberg equation. Remember, p squared plus 2pq plus q squared equals 1. Remember that middle term, the 2pq, represents that proportion. That's how many, or the proportion, of heterozygotes we expect under Hardy-Weinberg. So let's go ahead and calculate that. Remember, it's 2pq. P represents what? The allele frequency for A1, and Q represents the allele frequency for A2, and we know both of those values. So we would have what? We would have 2 times 0.5 times 0.5, and that gives us what? That should give us 0.5 if I've done the math correctly. So let's go ahead then and finish up by finally calculating F for this population. So that would be 0.5 minus 0.3, all divided by h naught, which is 0.5. And that should give us 0.4. So on our continuum of 0 to 1, right, 0.4 represents a fair amount of inbreeding. So based on our inbreeding coefficient, that's a fair amount of inbreeding. And that's not really all that unexpected, right? We kind of simulated a fair amount of inbreeding in this population. And this is the result that we get. Now I'd like to make one final point here, and that is that in this simulation we've used non-random mating and non-random mating patterns as our driver for inbreeding. But remember that inbreeding occurs when mated pairs come together and share genotypes that are more similar than what we'd expect by chance. But as you can imagine, random mating can still produce a certain level of inbreeding. So imagine our population here of 1,000 individuals, and let's say we've whittled it down to a population the size of 20 individuals. Among those 20, we could still have random mating occurring, but the chance that one mating event will involve mating between relatives is actually quite high, right? Just by virtue of being a small population. So the point here is that from a conservation perspective, a conservation biology perspective, as populations get smaller, we should expect a certain level of inbreeding, and that may be a consideration for management. Okay, so I'm going to hand you over to Terry now, and Terry's going to build a spreadsheet that will cover much of what we've talked about, and it will explore this relationship between genotype and allele frequencies and F statistics in much greater detail. So with that said, Terry, on to you.